my hope will never die.
The four-color theorem is a theorem in graph theory which states that any planar map or graph can be colored with at most four colors, such that no two adjacent regions or vertices have the same color. In other words, no planar graph or map, such as this map of the US, will ever have a chromatic number greater than 4. The four-color problem, sometimes called Guthrie's problem, was originally conjectured by Francis Guthrie in 1852, and was then introduced to Augustus de Morgan, who we know from De Morgan's laws. De Morgan, who was a professor at the time, then introduced it to the general mathematical community, where it stayed a hot topic for over 100 years. The first paper was written over 20 years later by Arthur Cayley, and the first two proofs took another year to come out. However, these proofs were later proven to be incorrect. It took until 1977 for a reliable proof to be developed with the help of a computer program. The theorem was proven again in 1996 and verified by Microsoft Research in 2004. Graph theory is the branch of mathematics concerned with networks of points connected by lines. The four-color theorem is an important part of graph theory and has applications in many different disciplines outside of mathematics. Graphs can be used to represent relationships between species, communication structures in social groups, and many other kinds of relationships.
The four-color theorem was proven using computers. Mathematicians used a software tool called Coq, which is an interactive theorem prover. The proof generated for the four-color theorem is a proof by exhaustion. We know that we can trust the proof because the program's algorithm tested every possible case, which there were several hundred of them, to confirm the validity.
Okay, so discrete math and the theorem. So this is specifically talking about the applications of the four-color theorem in discrete math. So one of the applications that it is directly applicable to will be graph theory, specifically finding the chromatic number of a graph, which is the smallest number of colors required to color the graph in a manner such that each vertex has a color different from all the other vertexes adjacent to it. For algorithms, we found Kemp's proof and Appel and Hacken. Talking about Kemp's proof first, this was one of the very first proofs for the four-color theorem. Originally, it appeared that there was no flaws in it. However, a decade after Kemp published this proof, another mathematician named Haywood found a flaw in the proof. Even though him and Kemp attempted to fix it, they were unable to do so. But after finding the flaw in Kemp's proof, later two more mathematicians named Appel and Hacken created another proof. So this is the only proof that has been able to solve the four-color theorem completely, or prove the four-color theorem completely. But it's a little controversial because Appel and Hacken used a computer to prove the four-color theorem, and additionally the fact that it had to be used on a computer, or had to be performed on a computer, I guess made people a little suspicious of calling it an actual proof. So, which is why today mathematicians are still debating whether or not Appel and Hacken's proof is a legitimate proof of the four-color theorem. However, this, until today, and I guess continuing, this has been the only method that has found a real proof for the four-color theorem. Most of the other proofs have had flaws.
The four-color theorem has a wide range of applications. The application most commonly thought of is the coloring of maps. For instance, you might want to color a map of the United States in such a way so that you can easily distinguish two states from one another. Something more practical for us is that we can also apply the four-color theorem to a graph for a cadet's T schedule. Each vertex of the graph represents a T. Each edge represents any time two T's must be taken by the same cadet, and the colors represents different time slots for the T's. The chromatic number is the number of time slots required for the t's. In conclusion, the four-color theorem is an integral topic in discrete mathematics and has countless applications.